with the tools at our disposal, we can now analyze projectile motion. So that's the motion of a projectile subject to the influence of Earth's gravity. It'll start with some initial velocity, and then we can figure out its path and how it behaves and all that just based on the information we already have. In doing so, what we'll do is we'll treat the horizontal motion as a constant velocity motion. So this is no acceleration, our velocity is constant. What that means is that my velocity at any time in the x direction is always equal to whatever velocity I started with. This is neglecting aerodynamic drag. So this is assuming that the air isn't having any effect. If you have the air slowing you down, then your velocity will slow. So that's not this. This model is assuming that aerodynamic drag is not important to this motion. So that's maybe not incredibly appropriate to soccer balls, depending on how fast you're kicking them. But it is fairly appropriate for a lot of motions we can look at. And then our final position will be whatever initial position we started at, plus our velocity times time, again, because our velocity is a constant. This is not true in general. Anytime you don't have a constant velocity, you wouldn't expect this to be true. But when you do have a constant velocity, it is. So there we go. We've got horizontal motion with constant velocity motion. And then our vertical motion will be constant acceleration motion, like in free fall, with a negative acceleration, so a downward acceleration of 9.8 meters per second squared. What that does is it gives us all of our constant acceleration equations applied with some subscripts to keep them distinct from our x direction expressions. So we get our final velocity is equal to vy naught minus gt. Our final position is our initial position plus our initial velocity in the y direction times time minus 1/2 gravitational acceleration times time squared. Our final velocity in the y squared is equal to our initial velocity in the y squared minus twice gravity times the quantity y minus y naught. And with those, we can resolve our motion onto our x and y axes and solve for what we want. So our strategy will be just doing that, resolving our motion onto x and y axes and treating the x motion and the y motion separately, solving for the unknowns that we want to know, realizing that at a given point in time, at a given position, our time is shared. So if we're considering a specific position, the time to get there has to be the same for the x motion as the y motion. And then we can recombine to get magnitudes and directions of whatever we want to analyze.